The second probe has been looking at Venus, and this is the impressive Galileo. Frankly, it wasn't meant to. Galileo is a Jupiter mission, and the original plan was to go straight from the Earth to Jupiter. But various cutbacks and difficulty with the launcher meant that the plan had to be altered, and Galileo's had to go by a much more circuitous route, rather like going to Bognor to Brighton via Carlisle. It's had to bypass Venus once and the Earth twice, and in passing Venus, it sent back some useful data. It's also been out into the asteroid belt, and there's been a successful pass last October of the asteroid Gaspra. But I'm afraid there are problems. The high-gain antenna has not deployed properly. Efforts have been made to free it. So far they've not been successful, but of course further attempts will be made, and we hope that by the time Galileo reaches Jupiter in December 1995, all will be well. The plan is to put the orbiter into a path round Jupiter to monitor the planet and also the main satellites, while the entry probe will detach itself and go straight down into Jupiter's outer gas, sending back invaluable information in the last few moments of its life before it's destroyed. So let's look forward to the arrival of Galileo at Jupiter in December 1995. Mars has always been regarded as the most interesting of the planets. In the 1960s, unmanned probes were sent there. And then, in the mid-1970s, came two Vikings, which made controlled landings on the Martian surface and sent back the first direct pictures. And this is a full-scale model of a Viking standing upon Mars. They looked carefully for any signs of life. They didn't find any. But many years earlier, in a Sky at Night program, we'd look forward to the possibility of life on Mars.
Now, you'll sometimes hear it said that there may be plant life on Mars. Well, it's rather unlikely, I think, that any of our higher terrestrial plants would survive under Martian conditions, although it's just possible that some very lowly forms, which we've not yet tested, may. But just to show you the fate of higher plants, I brought along tonight two cacti. And you can see these here. This cactus has been quite healthily growing under Earth conditions, and you see it's quite a nice firm-looking sort of cactus. This one here has spent one night under Martian conditions, and I think you can see without any doubt that it's got a distinctly morning-after appearance.
The myth of the Martian canals was finally laid to rest. And those dark areas were not old seabeds filled with vegetation, they were simply albedo features. But Mars did show massive volcanoes, and there were things there that looked remarkably like old riverbeds, indicating that there must once have been running water upon Mars. But life? Well, in the mid-1970s, the two Viking probes were dispatched, and they came down gently upon Mars and sent back information direct from the surface. And they looked very carefully for any signs of life. They didn't find it, and it does now seem that at the moment anyway, Mars probably hasn't got any life on its surface. It's interesting that although the Russians have had great success with their probes to Venus, they've had no luck at all with Mars, and all their various Mars probes have failed for some reason or other. Even their probes to the larger of Mars's two moons, Phobos. And the idea there was to land on Phobos and literally hop around the surface. But both those Phobos probes went out of contract, one because of human error, a faulty signal sent out from Russia, and the other because of a failure on the probe itself. There were great successes with the outer giants, Jupiter and Saturn. Both these were contacted by the pioneers in the early 1970s, but then came the Voyagers. Voyagers 1 and 2 were launched in 1977. 2 years later, Voyager 1 flew past Jupiter and then went on to a rendezvous with Saturn. Voyager 2 surpassed even this and was possibly the most successful spacecraft of all time. It flew by Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989. And the Jet Propulsion Laboratory here in California is still in touch with it.
Well, certainly at Jupiter, the highlight, the thing which caused the largest revolution in our thinking was the discovery of 8 active volcanoes on Io. And that, in fact, taught us how important evolution is in the formation and change in these planets. At Saturn, certainly, one of the major surprises was all of the fine structural detail that we discovered in the rings of Saturn. And, of course, there was Titan itself, where we measured for the first time an atmosphere 60% higher pressure than here on Earth, mainly nitrogen, with interesting hydrocarbon chemistry. There were two surprises at Uranus, at least. One was the fact that the magnetic field was tilted by some 60 degrees from the rotation axis, the first time we'd ever seen such a thing. And then there was the moon Miranda, a small world only 500 kilometers across, but which had experienced a very intense geologic activity sometime in the past, which significantly changed its surface. At Neptune, we had a number of surprises. So one of the surprises was it also had a tilted magnetic field, but perhaps the highlight of the whole encounter was the moon Triton, the first moon we've seen, which is so cold, almost 400 degrees below 0 Fahrenheit, so cold that the surface has solid nitrogen and solid methane on the surface, and the geology was reminiscent of many objects we'd seen before in the solar system.
Yet the Americans pulled out a one space mission on the grounds of expense, the mission to Halley's Comet. Comets, as I'm sure you know, are insubstantial bodies. Even a large comet is made up of a relatively small, icy nucleus, which starts to evaporate as the comet nears the sun, producing a head and a tail. The most famous of all comets is Halley's, which comes back every 76 years. Halley's comet returned in 1835 and in 1910, so it was expected back to perihelion, its closest point to the sun, in 1986. But to start with, no one knew how bright it was liable to be, and searches for it at all the major observatories began years ahead of time, way back in the 1970s. And when success finally came, the triumph was here at Palomar. With this great telescope, the Palomar 200-inch reflector, the comet was observed in 1982 for the first time since 1911. And surely it's fitting that the most famous of all comets should be recovered after more than 70 years with the world's most famous telescope. And, of course, this was the first return when Halley's Comet was observed by spacecraft. When Halley's Comet was recovered, it was a tiny, dim blur. Even when closest to us, in 1986, it never became bright. But all the same, this was a most important return. 5 spacecraft were sent there. 2 Japanese, 2 Russian, and the European spacecraft Giotto, masterminded from the operations center here at Darmstadt in Germany.
Well, everything went fairly well according to plan. We had beautiful data when suddenly, just 7 seconds before closest approach, the screens went blank. That was a major disappointment. Another thing that comes back to my mind is the colorful images of the near nucleus region, which were extremely difficult to interpret. And it was only at 2 o'clock, 3 o'clock in the morning of that night that we saw the first relatively clear black and white images, which showed the outline of the nucleus fairly well. And I remember at 3 o'clock in the morning I saw my first, as we then called it, crater on the surface of the comet. And for me this was the ultimate proof that we had actually seen the comet nucleus. The size of the nucleus from one end to the other is about 15 kilometers, the diameter 8 kilometers, and it has this odd shape. It is fairly dark, and it has some very interesting surface features, valleys, mountains, and so on. And to obtain these clear images of the nucleus, I would say, is perhaps the main achievement of the Giotto mission.
But we haven't heard the last of Giotto. It's been reawakened, and on the 10th of July it will encounter another comet, Grigg-Schellerup. What makes comet Grigg-Schellerup so interesting?
Well, we have visited comet Halley, and now we are visiting a comet which is of a different nature, insofar that Halley is a very active comet, ejecting a lot of gas and has a dust cloud around, whereas Grigg-Schellerup is much less active. It's also much smaller, only 500 to 2,000 meters. That's what the astronomers estimate. And it is interesting to compare both of these comets to see if there's any evolution and what causes difference.
How many of the original instruments are still working?
We originally had 11 scientific instruments on board, fully working. Now, out of these, 7 are still functional, and we hope, good scientific data.
Last time you went to within about 500 kilometers of your target, Halley's Comet. How close will you go this time to Comet Griggs-Shellerup?
We will aim direct at the comet nucleus, but we expect that we will pass within 1,000 kilometers of the comet nucleus.
At the technical headquarters of the European Space Agency at Noordwijk in Holland, many successful spacecraft have been built. The latest, Ulysses, was launched in 1990. Last time we were here, it was undergoing its final tests. It's now on its way to the Sun, having passed by Jupiter in February. Jupiter's powerful pull was used to swing Ulysses into the correct orbit for looking at the poles of the Sun. They've never been studied before, but why are they so important?
That is a very good question. As with the Earth, you have the polar regions and the equatorial regions. At the moment, every probe that has been launched, every spacecraft that has been launched, has been almost entirely in the ecliptic plane, and therefore we only get to look at the Sun sideways on. This has been likened by one of the experimenters that's flying on this to trying to understand the physics of the Earth by flying an aeroplane round and round the equator. The poles, just as for the Earth, where we only really understood how the northern lights occurred, was when we started flying spacecraft over the poles and understood how the magnetic field of the Earth worked. In exactly the same way, we need to fly over the poles of the Sun to understand how the Sun works.
It's amazing to think that you and I are standing within a few feet of a probe that's actually going to be launched and is going to go over the Sun in the near future, and I imagine you're pretty excited about it.
Oh yes, of course. One's always excited and scared too, because space is a risky business. You never know for sure whether it's going to work. There is nothing guaranteed in the space business. So it's a very exciting and very scary time for all of us.
From space, observations can be made which can never be carried out from the Earth's surface because of the shielding effects of the Earth's atmosphere. X-ray astronomy must be done entirely from space, and Skylab carried an X-ray telescope built at Birmingham University.
We've built two of them to go into orbit. The first of them was on the NASA Spacelab 2 mission in 1985. That instrument was taken into orbit and operated for about 10 days, and then finally brought back, and we refurbished it, and we're now hoping that we may be able to use it in the run-up to the space station. The second one was placed on the Mir spacecraft of the USSR. That's a space station, in fact, and is intended for long-term operation in space, and so we hope that telescope will go on operating for a considerable period, and it's already been operating for a couple of years.
And Britain had been involved in many other space ventures. In 1983 came the launch of a very special satellite, IRAS, the Infrared Astronomical Satellite. It was, of course, unmanned and was an international venture. The information was received and analysed here at the Rutherford Appleton Laboratory in Oxfordshire. It was the first satellite to discover a comet, IRAS Araki-Alcock. IRAS also found the zodiacal dust bands, which turned out to have considerable structure, probably linked to asteroid families. It found a dust ring around the star Vega, where planets failed to form. It saw stars all the way to the centre of our own galaxy. It found stars forming in galaxies much brighter than ever imagined in the infrared. And the cirrus, the infrared dust in our galaxy, which has obscured the view of stars in the same way as cirrus clouds obscure the view from Earth. As IRAS was only designed to last for 9 months, were the astronomers surprised at the wealth of data?
I think we were very surprised at first. You know, before IRAS was launched, at the longest wavelengths you can easily observe from the ground at 11 microns, we had about 2,000 sources known. IRAS in the first 12 hours of operation discovered over 3,000, and so that was a real surprise. I think we were all rather overwhelmed.
There are infrared telescopes on the Earth's surface. Why do you have to go into space?
Well, there are a lot of regions that we want to look at, particularly IRAS showed this, that you can't see from the ground. All these marvellous galaxies we found in these dust shells, they are most bright at wavelengths longer than the ground can observe. And so we really need to go into space. And of course, with our new satellite, the Infrared Space Observatory, we can look at things that we discovered with IRAS, and we can look in the wavelengths that we can't see on the ground, and hopefully we'll find a lot of new objects there.
IRAS can do things that no ground-based equipment can do because it's moving above the top of the atmosphere. We now have infrared maps of the whole of the sky. But we also need very accurate maps of things we can see visually. We want to know the precise positions of the stars, and we want to study the ways in which the stars move individually. This can be tackled from ground level, but again, we've been overtaken by space research on a satellite, Hipparcos, built at Noordwijk by the European Space Agency. Actually, Hipparcos was put into the wrong orbit because of a faulty rocket firing, but nevertheless, it has been able to carry out its full program of research.
By measuring the positions very accurately, we can eventually determine the distance to the stars and how the stars are moving through our galaxy. And very many areas of astronomy and astrophysics actually depend rather critically on a detailed knowledge of the distances and the motions of the stars. So this is really what we're trying to get out of the measurements.
Why have these measurements got to be done from space?
The Earth's atmosphere acts as a screen which affects the incoming light and makes the possibility of measuring very accurately the star positions rather difficult from the Earth. By moving above the atmosphere, we can measure these positions much more accurately. The second reason is that the environment above the atmosphere is very good for these kind of observations, both from a thermal point of view. We can have a very constant thermal environment on the satellite, and from the point of view of the effects of gravity on the instrument. The third reason is so that we can achieve an all-sky visibility. Measurements which are made from the ground can only be made viewing a certain part of the sky if you're in the northern hemisphere, or the southern part of the sky if your observatory is in the southern hemisphere, and we can only observe certain parts of the sky at certain times of the year from the ground. And this makes the construction of an overall system of positions and motions very difficult to achieve from the ground.
Hipparcos has been a major success of visible wavelengths. We've also had major successes in what we may call invisible astronomy, with, for example, IUE and IRAS. But let's not forget the advantages of space for conventional telescopes, which are unconventional only inasmuch as they operate from above the top of the atmosphere. 1990 saw the climax of one of the most ambitious space projects yet. I'm at the Johns Hopkins University in Baltimore, or, to be more precise, at the Space Telescope Science Institute. At the moment, this is one of the most important places in the scientific world. It's the nerve center of the most fantastic telescope ever planned, the HST, or Hubble Space Telescope. Operating from above the atmosphere, the HST has perfect seeing conditions all the time, which is why, even though it has only a 94-inch mirror, it can outmatch all the larger telescopes based on the surface of the Earth.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
It was a perfect launch. Once the telescope was in orbit, tests began. That, of course, was the moment when it was discovered that the mirror was faulty. And it was a most unpleasant shock.
Well, you know, Patrick, we used to say that this mirror is the most finely polished mirror ever built, and that's still true. We used to say that it was the cleanest mirror ever made, and that's still true. It's simply apparently machined the wrong shape. The prescription is incorrect by about 2 microns, which in English would be about 1/50th the width of a human hair. There are 2 ways to get around this particular problem. One way, which we are addressing now, is to use computer algorithms, or reduction tricks in effect, to massage the images to remove the halos. It's a process of deconvolution, the $50 word, or image enhancement. The real way to solve this problem, of course, is to get back to Hubble and to put a series of corrective lenses and mirrors on the telescope to introduce an equal but opposite amount of aberration. That we hope to do within a few years with some astronaut help on board the space shuttle.
Objects of all kinds were imaged. Jupiter with its cloud belts. Saturn, obliging enough to produce a brilliant white spot at just the right moment. The cores of globular clusters, such as 47 Tucani, with the stars called blue stragglers. The light ring from the supernova in the large cloud of Magellan. and the effect of a gravitational lens with the light from a remote quasar split up by a foreground galaxy to produce the Einstein cross, or cloverleaf. Well, you can see how much has happened during the 35 years since the Sky at Night went on the air and Sputnik 1 was launched. We've had satellites of all kinds, probes of planets, men on the moon, and our knowledge of the universe has grown beyond all recognition. But what of the future? Probes are planned for Venus, Mars, Jupiter and Saturn. By the year 2000, we may well have permanent space stations, perhaps even a base on the moon. And think how quickly all this has happened. The first airman, Orville Wright, made his preliminary flight in 1903. The first man in space, Yuri Gagarin, went up in 1961. And the first man on the moon, Neil Armstrong, landed there in 1969. So in only 66 years, man has gone from being earthbound to flying to the moon. And now there are spacecraft traveling beyond the solar system. So I wonder what's going to happen during the next 35 years. I'm afraid that I won't be presenting the Sky at Night in 2025, unless, of course, I live to the advanced age of 102. But I'm quite sure that it's going to be dramatic. Here, from my little observatory in Chelsea, I've seen what's been going on, and I've tried to share it with you. Thank you for watching. But you know, although in this program we've seen many sophisticated spacecraft, I still have a soft spot for one that I personally test-piloted a few years ago. As you can see, the design of this lunar bicycle, in which I'm riding at the moment, differs in certain important respects from that of the lunar rover, and is fairly obviously superior to it because it contains a number of features not previously incorporated. This, as you can see, works very much in the manner of a sweeper, and this is precisely what it is, and this will collect lunar samples for you. Next, we have the lunar boot. It can be used to plant the usual obligatory footprint upon the moon's surface, just in case the pilot is too tired to get out of his bicycle. But of course, future astronauts will in fact be able to incorporate these lunar bicycles, which do make the present lunar rover completely obsolete.